Assalamualaikum warahmatullahi wabarakatuh. So this is the video for chapter 4.3, which is on analysis of heat exchanger. The objective for this chapter 4.3 is first, students should be able to perform general energy analysis on heat exchanger. Second, students should be able to obtain a relation for the logarithmic mean temperature difference for use in the LMTD method, and modify this LMTD method for different types of heat exchanger, for example shell and tube, cross flow heat exchanger, using the correction factor. Next, students should be able to develop relation for effectiveness and analyze heat exchanger when the outlet temperatures are not known, using effectiveness NTU method. Lastly, students should be able to know the primary consideration in the selection of the heat exchangers. Now let's have a look on this analysis of heat exchanger. So we have two different design tasks. First one, the designer is provided with the temperature change in a fluid stream and also the mass flow rate, and the designer need to select a heat exchanger. So second design task is the designer provide with the information of the heat exchanger type and size, fluid mass flow rate, and also inlet temperature. And the designer need to predict the outlet temperature and also heat transfer rate. So the two methods used in the analysis of heat exchanger is, first one is log mean temperature difference, which is LMTD. Second one is effectiveness NTU method. So this NTU is referring to number transfer units. So basically for the LMTD is best suited for the design task 1. Meanwhile, for the effectiveness NTU is best suited with the design task 2. So basically in the question, if you're given with the temperature change and also mass flow rate unit, you can use the LMTD method. So for the NTU method, normally in the question given the heat exchanger type, mass flow rate, and also in the temperature. So you can use the effectiveness NTU method to perform your calculation. So the analysis of heat exchanger can be greatly simplified by making the following assumption, which are closely approximated in practice. So first thing is steady flow. So second one is kinetic and potential energy change are negligible. So next, the specific heat of a fluid is constant. The axial heat conduction along the tube is negligible. So this one we assume that the heat transfer is in one dimension. So next, the outer surface of the heat exchanger is perfectly insulated. The first law of thermodynamics requires that the rate of heat transfer from the hot fluid equal to the rate of transfer to the cool one. So Q for the hot fluid is equal to the Q of the cool fluid. So for the heat transfer rate for the cool fluid, we can use this 11.9 equation, which is Q is equal to M C specific heat C PC times with T C out minus with T C in. So this equation can be simplified by using the heat capacity formula. The heat capacity is equal to mass flow rate times with specific heat capacity. So the next formula that we can use is the transfer rate to the hot fluid, which is Q is equal to mH CPH time with TH in minus TH out. So these two actually is a heat capacity. So the equation can be simplified as shown in 1113. Okay, for your information, the Q is a positive quantity. The direction for this Q is from the hot fluid to the cold fluid. So this direction of the heat transfer is mentioned in the second law of thermodynamics. So there is two special type of heat exchanger commonly used, which is condenser and also boilers. So these condenser and boilers undergo phase change process, and for the rate of heat transfer formula that can be used to calculate it for the condenser or boiler is Q is equal to mHg, whereby this H is a heat of vaporization. So now we move to the log mean temperature difference method. So this LMTD method is a temperature difference between the hot and cold fluid varies along the heat exchanger. So for this method, it is convenient to have a mean temperature difference Tm. So our heat transfer rate equation, we can put in the mean temperature difference here. So consider the parallel flow double pipe heat exchanger. So this one. So this is double pipe heat exchanger. So parallel flow, like what we learned before, the end for the hot and cool inlet is at the same end, hot and cool out at the same end, and the direction of the flow is in the same direction. So an energy balance on each fluid in differential section of heat exchanger can be expressed by like this. This is the energy balance equation. So for 1116 is for the hot fluid, 1117 for the cold fluid. So this equation we rearrange it, and we can have like this: delta TH is equal to negative Q over mH CPH. Why we put it as negative? Because we can see from this graph, for the hot fluid, the energy balance, we can see this graph is decreasing, right? So that's why it is negative. So for the cold one, the graph is increasing. So this is positive value. Okay. So another information for you, for delta T1, we consider TH in with TC in. Meanwhile, for delta T2 is the difference between TH out and also TC out. So taking the difference from above, from this equation, we can get, so this del TH minus with del TC, we can have, so when we minus it, we can have this equation. So this is minus also, can get 1120. So the rate of heat transfer in the differential section of heat exchanger can also be expressed as Q U delta T dA. So just now we have a energy balance equation. So instead of energy balance, we can use this formula. So now we have to get the relation between those two formulas. So we substitute the equation 1120 and 1120 into this 1121 and rearrange it. It will give this kind of formulas, which is equation 1122. So in the next slide, I will show you one by one how you can get this formula. So we need to integrate this 1122 from the inlet to the outlet, and we can obtain this 1123. So in the next slide, we show you the derivation on how to get 1122 and 1123. Okay, basically from 1121 we have del TH minus TC is equal to del Q 1 over MH CPH plus with 1 over MCCPC. So rearrange this equation. Del Q is equal to del TH minus TC over with 1 MHCPH plus 1 over MCCPC. So from 1120, just now is 1120. So from 1121, so we substitute this one to 1121, which is TH minus TC over with 1 over MH CPH plus 1 over MCCPC is equal to U TH minus TC del AS. Okay. So now del TH minus TC over with TH minus TC is equal to U 1 over MHCPH plus 1 over MCCPC del AS. So integrate both sides. So this is from in to out. So integrating all of these, we will get ln, right? So we will get ln TH out minus TC out over with TH in TC in. Okay. So please remember this one, we still have negative, right? So this is here is negative. So negative UA time with MH CPH plus 1 over MC CPC. So same, right? 1123. So this is how you can derive from 1120 substitute with 1121 and you get 1123. Okay, so solving equation 11, 9.9 and 11.10 for MC, CPC and MH, CPH and substitute into equation 11.23 that we derived just now, we will have 1124 and 1125 whereby delta T log mean temperature temperature here is equal to delta T1 minus delta T2 over ln delta T1 over delta T2. So later on the next slide, I will show on how to derive for this one also. So delta T log mean, this is the this is the log mean temperature difference. So delta T1 and delta T2 are the temperature difference between two fluid at the two ends, like what I'm showing in the previous slides at the figure of the double heat exchanger just now. So basically, if you change the end of the inlet or outlet, actually there is no difference of the temperature difference. Okay, so basically this is the derivation on how you can get 11.24. So basically we use equation 11.9 and 11.10 to rearrange this formula and we will get, MC CPC here is equal to Q over TC out minus TC in. So this one MH CPH is equal to Q over TH in minus TH out. So from the 1123 we have this ln. So just now in 1123 we have this one 1 over, we have this one, right, 1 over MH CPH plus 1 over MC CPC. So we substitute the equation that we write this one into the 1123 and we will get TH in minus TH out. This one, so previously is MH CPH, right? This one MC CPC. So just substitute. So if we substitute this one into this, this one into this one, the Q will become the like this and this. Okay, after you substitute like this, rearrange back the Q, make it the left hand side as a Q is equal to UA times with this TH in minus TH out plus TC out minus TC in over with this. So this one basically come here, Q here. So the summation of all of this is here. Okay, so rearrange back the inlet with the inlet, hot fluid inlet, cold fluid inlet, the outlet with the outlet. That means cold fluid outlet, hot fluid outlet. So here we can see that this is inlet delta T1, right? This one is delta T2. So this one is delta T2. This one is delta T1. So basically we will get this 11.24 formula. So for the delta TLM basically is this one. Okay, I hope you clear with this derivation. So now we move to the counter flow heat exchanger. So the relation already given for the log mean temperature difference for parallel flow heat exchanger can also be used for the counter flow heat exchanger. So for the delta T1 and delta T2 are expressed as shown in the figure here. So just now we have delta T1 for the parallel flow. Delta T1 is delta TH in minus TC in, right? So for the counter flow, we need to change because the end here is between H hot fluid in and cold fluid out. So we just need to subtract TH in with TC out. For the delta T2 is TH out with TC in. So basically, the log mean temperature for the counter flow is basically greater than log mean temperature for the parallel flow. A smaller surface area, smaller heat exchanger is needed to achieve a specified heat transfer rate in the counter flow heat exchanger. This is because this delta T log mean is bigger, so that's why we need a smaller size of heat exchanger for the counter flow. So for the multi-pass and cross-flow heat exchanger, we can use the formula for log mean temperature just now, LMTD method just now, but we need to multiply with the correction factor. So to simplify the analysis of cross-flow and multi-pass shell and tube heat exchanger, it is convenient to express the log mean temperature difference relation as delta TLM is equal to F, which is correction factor, time with delta TLM. So the F here is a correction factor. So we need to time with the delta TLM for the counter flow case. So basically for the cross flow heat exchanger and shell and tube heat exchanger, the correction factor we can obtain from this graph. So basically you need to calculate the value of R and also value of P based on the information given in the question. So basically for capital T is at the shell side, the small t at the tube side. So by calculating this R and P, you can have the value of correction factor. For example, you get the P is around 0.4 here, and then your R is 1.5. So you just draw the straight line here to the pink line, and then move the line to the y-axis, and you will get the correction factor, which is 0.8. So this first graph is applicable for the 1 shell pass, 2, 4 and 6 tube passes. If you have 2 shell passes, 4, 8, 12, any multiply of 4 tube passes, then you can use this graph. For the cross flow heat exchanger, we have two types, which is single pass cross flow with both fluid unmixed, and single pass cross flow with one fluid mixed and the other unmixed. So based on the question that you get, and based on the type of heat exchanger that you get, you need to refer to the correct graph so that you can get the correct correction factor. So basically for the cross flow heat exchanger also you need to calculate R and P to get the correction factor. So the heat exchanger design procedure using the LMTD. So with LMTD method, the task is to select a heat exchanger that will meet the prescribed heat transfer requirement. So the procedure to be followed by the selection process is first, select type of heat exchanger suitable for the application. Second, determine any unknown inlet or outlet temperature the heat transfer rate using energy balance. So this is you can use QMCP delta T. So third step is calculate the log mean temperature difference, which is delta TLM, and the correction factor if necessary. This one if you use shell and tube and also cross flow exchanger. So number 4, you need to select or calculate the value of overall heat transfer coefficient, which is U. And lastly, you have to calculate the heat transfer surface area needed to meet the requirement. For the effectiveness NTU method, basically this method is a dimensionless parameter based on the dimensionless parameter, which is heat transfer effectiveness. This one. So for this NTU method, for the effectiveness, you can calculate by divided the actual heat transfer rate with the maximum possible heat transfer rate. So for the actual heat transfer rate, you can use the heat balance equation, Q equal to MCP delta T or C times delta T. So basically, the maximum temperature difference is delta T max is equal to H in minus the temperature of the hot fluid in minus with temperature of the cold fluid in. So basically, the maximum temperature difference you can get from this inlet pipe. Because at first, before the heat transfer occurred at the inlet, the difference between the hot fluid and the cold fluid is greater, right? So that's why we can get the maximum temperature difference at the inlet side. So maximum possible heat transfer rate in a heat exchanger, we can use this formula whereby Q max is equal to C min time with delta T max. Okay, what is C min? So basically we have the heat capacity for the cold fluid and also heat capacity for the hot fluid. So basically between when we calculate the heat capacity for both hot and cold fluid, we see which one is the lowest, which one is the smallest. So from here, after calculate, we obtain CH is the lowest, which is 92. So this one will be the minimum heat capacity. So after get the minimum heat capacity, you will need to calculate the maximum delta T, and you can get the value of the maximum heat transfer rate. So once the effectiveness of the heat exchanger is known, the actual heat transfer rate can be determined from, so if you're given with the effectiveness and you already calculate the Q max just now, you can get the actual heat transfer rate. So basically the effectiveness of heat exchanger depend on the geometry of the heat exchanger and also the flow arrangement of the heat exchanger. This one, if I'm not mistaken, already learned inside chapter 3. So it can be shown that the effectiveness of double pipe heat exchanger for the parallel flow is So basically for the parallel flow, if you want to calculate the effectiveness, you can use the equation in 11.38. So effectiveness relation of heat exchanger typically involve dimensionless group called the number of transfer unit NTU. So basically NTU is equal to UA over MCP mean. So this one actually you already learned inside chapter 3 on how to get this, to derive this formula. So for specified value of U and C mean, the value of NTU is measure of the heat transfer surface area. So for your information, the larger the NTU, the larger the size of heat exchanger. So instead of an NTU for the effectiveness, we need to define the capacity ratio C. So the capacity ratio is the heat capacity minimum over with heat capacity maximum. So basically the effectiveness of heat exchanger is a function of the number of transfer unit NTU and also the capacity ratio C. So basically to calculate effectiveness inside it, we'll have the NTU and also capacity ratio because this effectiveness is the function of these two. So basically like what I'm saying before, this one you can derive. Basically this one already show inside the chapter 3, so I just taking back the information from the chapter 3. So basically you have a energy balance equation here, and you have Newton of cooling here. So using these two equations, rearrange it by this one, assume is equal to A is equal to P times dx. So rearrange the equation. This one, this Tm is equal to Ts minus Tm, and then you will have this kind of equation. So integrate both, you will get ln pi and also this one. So basically this one is NTU. So to calculate, to know the NTU, you can calculate, you can substitute this value, this value, this value, and this value. So for the effectiveness for several heat exchanger, just now I already show for the parallel flow. Basically, different type of heat exchanger will have different effectiveness relation. So depends on the type of heat exchanger you use. You just can directly take the formula in the table 11.4 here. So for the NTU, you can use this formula UA over C min, and for the capacity ratio, C min over C max. So substitute the value here and value here, you will get the effectiveness value. So for the effectiveness, also we have a graph in order to define the effectiveness. So here you need to have NTU. From the NTU here, let's say your NTU is 2 and your capacity ratio is 1, and then you will have the effectiveness is around 50 here. So each type of the heat exchanger will have a different, will use a different graph. So you can choose the graph based on the type of heat exchanger that you use. So selection of heat exchanger. An engineer going through catalog of heat exchanger manufacturer will be overwhelmed by the type and the number of readily available of the shell shaft heat exchanger. The proper selection depend on several factors. It's not we not just depend on the heat transfer rate. We also depend on the cost, for example, procurement, maintenance, and power. Other than that, we depends on the pumping power, size and weight, type, and also material. So other than that is miscellaneous, for example, leak type, safety, reliability, quietness. So basically, this is the factor that we need to consider on selection of heat exchanger.